This problem is about a spit take. If you aren't aware, according to the Oxford English Dictionary, a spit take is an act of suddenly spitting out liquid one is drinking in response to something funny or surprising. So maybe you've seen a spit take before. So in this spit take, a gauge pressure is applied to fluid in the mouth, P1, which is what we're looking for, so that it flows through the pursed lips, forming a column of liquid of radius 4 millimeters that shoots out at 3.1 meters per second. So the question is, in the mouth, it's 10 times larger than the pursed lips, so 10 times larger than that, R2, 4 millimeters. What pressure did it take to achieve this spit take? So in terms of fluid mechanics, here we have fluid that is flowing, so we have to use the Bernoulli equation. That's our main equation we've derived for a fluid that is actually moving. So let's think. So spit take here. So here, okay, this isn't good. So here are the lips making the little pursed 4 millimeter tube, and the liquid comes out here, and there's the chin, and that widens to the mouth that we said was 10 times larger area like that, and then it goes down wherever. So we're saying, it's not too bad, what's going on there? We're saying that in the mouth is here, we'll call that 1. I kind of use the number, the subscripts are kind of letting you know where everything is. 1 is the mouth, and 2 are the lips. The mouth is a little far back in the head here. Okay, so what we got to do is apply the Bernoulli equation, and the way it works is you have this thing that is constant. So we'll write it here in the mouth, and we'll write it here in the lips. The lips are 2, the mouth is subscript 1. And the thing, as I so elegantly described it, that is constant, it's the pressure. So the pressure at 1 plus a term that represents the gravitational potential energy of the fluid, the density of the fluid, G, and then how high it is in region 1, and then a term that represents the kinetic energy of the fluid, 1/2 rho V, the speed in region 1 squared, the fluid flow rate. So we got this just by thinking of conservation of energy for the fluid. This is how much work you're doing on it, and its potential, gravitational potential, and its kinetic. And what we decided was this is constant for any point in a flow for an uncompressible, no viscosity, yada, yada, yada. Okay, so for under our assumptions, we said this is constant. So we can write the same expression on the right side for the lips. The pressure, we're actually saying, when we say 2, we're actually saying as it exits the lips. That's going to be important in a minute. So the pressure at 2 plus the rho G, the height it is at 2, plus 1/2 rho and how fast it's going at 2. So this thing doesn't change throughout a flow, so you can pick any 2 points in the flow, and you have to get the same value for this expression. Expression, that's the word I was looking for, instead of thing. Okay, so now can we figure out what to plug in to all these parameters from our little story up here? All right, well, let's see. One thing, as we point out, we use the word gauge pressure. It's a little ambiguous. Is there atmospheric pressure in your mouth when your mouth is closed? We're going to say yes, because your cheeks are soft. So the atmosphere pushes on your cheeks, and your cheeks push on the cavity in your mouth. So really, if we want really the pressure at P1, it's atmospheric pressure plus, I'll write a little P1. Right? That was capital P1. That was the total pressure. Now I'm going to break it up into the atmosphere and the gauge pressure, because that's a little p also. All right, so that's how we think about that. It's the gauge that we're applying, gauge pressure we're applying, plus atmospheric pressure, plus, we do know these two numbers. We know the density of water. We're assuming this is water, by the way. And we know G, but here we have H1. We weren't really given a height. And also notice over here, we weren't really given the height here. And when you think about flow, you think about the center of the flow, and you could draw a line like that if you start thinking about the heights. And the point I'm getting to here is that this is a horizontal flow. There's no height change in the flow. So there's really no gravitational potential to think about. So basically these two terms are the same. So you just cancel them. this problem isn't about height. There's another problem later about flow uphill, and then the terms will matter. But these two go away because basically H1 equals H2. That's why these two terms are canceled. The flow rates are different though, so that's where we're going to get some interesting parts here. So we have 1/2 the density of the water, and we have the speed it's moving in the mouth, which we don't know. Interesting, V1 squared. Okay, so we have the left side, and now on the right, this is where it gets into little details about flow problems that you got to know. If you have some container, a head, lips, a bucket with a hole in it, whatever it is, and you're asked to talk about or to calculate about the flow right as it exits the container, then as soon as it exits the pursed lips, it's at atmospheric pressure. So the pressure we put here is just atmospheric pressure. There is no higher pressure like a gauge pressure applied to it because there's nothing that can apply it. Once you escape the lips, there's nothing pushing. So it's at atmospheric pressure. But what you can imagine is as it comes out, it doesn't spread out immediately. Right as it comes out, it's still the diameter of the lips, the pursed lips. But we're saying technically it's once you've exited the pursed lips. So that's why you have atmospheric pressure, is because we're outside now. And that's why I point out we're getting the pressure here, not in the lips, but right outside the lips. Plus 1/2 and the density of water, times V2 squared, which that one we do know. Okay? So you can see now what's going to happen. The atmospheric pressures cancel. We're really just thinking about gauge pressure here. The gauge pressure outside now is just 0. It's just an atmospheric pressure. But let's think about these terms and what do we know and what do we not know. This is what we're looking for, right? This we know. We know rho. So we could calculate as we go here. We know V2, that's how fast it came out. Right? So it looks like we don't know V1. We don't know how fast it's moving inside the mouth, but we can get it because it comes from continuity. Get V1 from continuity. And recall, continuity just means since the fluid is not compressible, that the areas and the volumes go together. A1 V1 equals A2 V2. So if this area gets small, the velocity has to go up. Okay, so we would say A1 V1 equals A2 V2. Now let's see, cross-sectional areas. We could calculate this one. It's pi r squared, where r is 4 millimeters. We actually don't have to do a lot of calculations because we were told what we need to know is that the column's area is 10 times larger inside the mouth than at the lips. So basically we know A1 over A2 is 10. Okay, so A1 over A2 is 10, so V1 is 1/10 of V2. Okay, so V1 is 1/10 of V2. So what we could then do is go in here and say 1/10 V2 squared. And then now we know V2. Okay? So it's really just Bernoulli, get rid of the atmospheric pressure, get rid of the potential energy term. You're almost there, you just got to use continuity to get the other V. All right? And then we're down to just plugging in P1 plus 1/2 1,000 times, what is that? That's 3.1, now it's 0.31. 0.31 squared equals 1/2 1,000, 3.1 squared. And if you work your way through all that, you get that really it's all in this term. This term is very big. This term is very small because the 0.31 versus the 3.1 is really all it ends up being. And you get 4757. So P1, the answer you'll get if you run those numbers, see that's a little P1, is 4757. And since we did everything in MKS units, that's in Pascal. Newton per meter squared. Which sounds like a lot, 4,000. Remember, that's newtons per entire meter squared. That's not a real high pressure. Atmospheric pressure, 101,325 or whatever. So that's only 4,000 instead of 100,000. So a very small fraction of atmospheric pressure to pull off a spit take of this quality.